In this lecture, we will see how to design gray code to binary code converter, right? It is also a combination circuit which will perform the code conversion, that is gray code to binary code. First, we will see what is the procedure to convert from gray code to binary. So this procedure we discussed when we discussed the number system. Now, whenever suppose we are having gray code, that is G2, G1, G0, which is 3-bit. If I want binary, what is the procedure? So MSB, that is so B2 is same as G2, that is same MSB will be follows. To get next MSB from the binary, so what we need to do is we have to perform the XOR operation between the resultant and the next MSB in the given gray code, that is B2 exclusive or G1, or we can say simply addition. So whenever we are doing the addition, that will perform by the XOR gate. Similarly, if I want the last LSB, I have to use this resultant and the next MSB in the given gray code. So this is like XOR gate function, XOR function. So this will give the next MSBs. Now if I take the example, then it will be very clear. So this is a given gray code. So if I want binary, the MSB will be as it is. To next get MSB, we have to perform the addition between this resultant and the next MSB in the gray code. So 1 plus 0 or 1 exclusive or 0 will get 1. Similarly, next one. So what is the exclusive or? 1 exclusive or 0 is nothing but 1. So for the gray code given 100, what is the equivalent binary? It is 111. Similarly, if you convert back, I'll get this one only. So this is a binary. We know the procedure to get the gray code, that is MSB as it is. To get next MSB, we have to perform addition. That is 1 plus 1 or 1 exclusive or 1, you will get 0. Then to get next one, we have to add these two or perform the XOR operation. So 1 plus 1 again, you will get 0. See, gray code, then binary and so on. So this is the operation. Now we need converter. So what we need to do, we have to form the truth table for 3 bits. So these 3 bits are input, or we can say sometimes XYZ or ABC, whatever. So this is a gray code. So I have given as G2, G1, G0. So this is a binary number or binary code. That's why I have given B2, B1, B0. Now we know the functionality of this conversion. So what we need to do for 0, 0, what is the value will get binary 0, 0 only, because MSB as it is. To get next MSB 0 plus 0 and so on. Similarly, as it is 0, so 0 plus 0, 0, 0 plus 1, 1. Similarly, 0 as it is, 0 plus 1, 1, 1 plus 0, 1. Next 0, I'll write the all ones. Next, to get next MSB, resultant plus 1, 1, resultant plus 1, 0, 1 plus 0, 1, 1 plus 0, 1. Next, 1 plus 0, 1, 1 plus 1, 0. When you do the addition, so 1 plus 1 will become 0. But when you perform the OR function, 1 plus 1 will become 1. So this is addition, remember. Next, MSB 1 plus 1 will get 0. Then 0 plus 0, 0. Next, 1 plus 1, 0. 0 plus 1. So this is the truth table for the gray code to binary. So we know the truth table. Then what is the next step? So we need to find the logic expression. Now using the K-map, we can find the minimized logic expression. So what we need to do? We need to map this truth table. See, whenever we are having 3 or more than 3 variables at the output, so we'll get 3 functions, 4 functions and so on. So that's why we'll get 3 K-maps. Now what we need to do? We have to map. Now if we see the first logic function, that is B2, it is just following the G2, right? So no need of any K-map, or we can even if you use K-map, first 4 zeros, then 4 ones. Even if I make a quad, so what I will get, this is B2 output function is nothing but G2 only, right? So no need of any K-map. If you see this truth table also, so whatever the G2 value, same we are getting here. So that is the one. In the next case, 00, 4 ones and 00. So how can I map here is 4 00, then 2 ones, then again 2 ones, then 00, right? So you can map like this. So or we can say these are the min terms, right? 0 1 2 3 4 5 6 and 7. So corresponding here is 0 1 2 3 4 5 6 7. Now what is the next step? We have to make combination. So I can make only 2 pairs. So what is this? B1. How can I write? So if I see this pair G2 into, in this 2 which one is common? G1 bar, plus in this 2 G2 bar, in this G1 is common. So what is this expression? It is nothing but exclusive OR function of G2 and G1. Yes or no? Then the last one is B naught. If you see B naught, 0, 1, 1, 0, 1, 0, 0, 1. It is nothing but, if you observe, this is, when you see the full adder, this is the full adder sum function. See, whenever there is an odd function, we are getting high value. I mean the logic 1. See, 1, 0, 0, we are getting high. 2, whenever 2 ones are there, so we are getting 0, and 3 ones odd function. So what is the odd function? It is nothing but exclusive OR function. So this is 0, 1, 1, 0. Then see here, 1, 0, 0, 1, 0, 0, 1. So this is the K map for this B naught. Now we cannot make any pairings here. So I can write directly, this is B naught is equal to the min terms I can write. So G2 bar, G1 bar, G naught. See, G2 bar, G1 bar, G naught plus G2 bar, G1, G naught. So this is 0, 1, 0. This is 0. Next plus this 1, 1, 0, 0. G2, G1 bar, G naught bar. This is 7. So G2, G1, G naught. Or we can write simply, this is the odd function. So who is the odd function? Nothing but exclusive OR function. G2, exclusive OR G1, exclusive OR G naught. So these are the logic expressions we got. So what is the next step? Next step is simply giving the logic diagram. So these are the logic expressions we got for this gray code to binary converter. Now what we need to do? So this is G2. So what is the B2? So there is nothing, no gate is required. So directly it is passing. Next, to get B1, so I need to perform the exclusive OR gate or exclusive OR function of this G2 and G1. So to get B naught, what we need to do? We need to perform the exclusive OR operation of these three. So already we got this exclusive OR gate. So what we do? One more exclusive OR gate is enough to find this B naught. So this is the G naught. So this is the simple logic diagram of this gray code to binary converter. Now we can go for the 4-bit gray code to binary, etc. Right?